So hi, thank you for joining. I'm very happy to be here in Moscow in this .Next event. That's great because I never expected in my life to come in Russia. I don't know why, but I feel a bit lost because I don't speak a word of Russian also. But I enjoy my journey so far here. I hope that you won't be lost by my slides and you won't quit the room too quickly. But anyway, I'm very happy to be here with you. So, my name is Alexander. So when I was a teenager, I used to program in assembly languages to push the limits of what you could get from the tiny CPU and RAM that we had in that time. And when it went a bit more serious, I was developing business application in Java. And around 10 years ago, I started to use C# and the C# language, the .NET ecosystem, and so on. And actually, I discovered that it was providing most of the things that I was looking for about combined productivity and performance for a language and an ecosystem. And but then I worked across the years during using, like, for example, for SharpDX project and so on to still push the boundaries of what I could get from C#, and but I knew that it was not enough. So when I was contacted 2 years ago by Unity to work on a new compiler technology that could unlock these last bits of performance, I was super happy to work on this, and here we are with Burst. So in this talk, I would like to get more to get more insights about what's the magic behind the Burst compiler. So from a .NET developer perspective, you will better understand the comparison, for example, with the existing code gen that we have in .NET, and what could be a future for code gen. So it's a talk about sharing what we have been doing and to inspire. I think that it's great that we have this at Unity. Maybe you would be very annoyed that it's a Unity-only thing, but by sharing it here today with you, I hope that we will be able to bring it to the .NET ecosystem at some point. So in the first part, I would like to go through all the original reasons of this project. And then we will see how Burst is working, how it is working, how it has been developed, how it's tested, how the integration in the Unity editor is working, the JIT, the AOT, and so on. And then we'll talk more about the optimizations that we can have, optimization. And in the final part, I will just give you a glimpse about what we are going to work in the future. So, why Burst? So it's all about performance. And so that was a demo that was done last year at one Unity event, Unite Europe, in Europe. And so you will be able to watch the YouTube video at some point. But that was an example of going from here on the top left, a single-threaded running with a mono runtime. So it was like 2,000 agents and one core, and it was running at 69 FPS. So it was showing lots of things running and moving around in the screen. And then the CTO showed that we have a job system in Unity, and we can parallelize stuff. And with 8 cores, we are going to be able to maybe move 10 more agents on the screen, and by using the CPU, all the cores of your computer, it's going to still to run at 46 FPS. And then he showed that by multiplying by 10 the number of agents and using what was a preview and alpha stuff of Burst, we were able to run 200,000 agents in real time, moving them all around in 50 FPS. So this is the kind of performance that we are talking about, the kind of gap that you can have when you care and you design and you have a good code gen and the data that are working together for this kind of workload. So there are like two aspects that are very important for Burst. The first one, of course, is the code gen, and we want to be able to be as fast as C++, at least as fast as C++. And we know that Mono, because Mono is mainly used in the Unity editor, for example, is slower than C++, of course. But even like .NET Core CLR, even if we don't use it at Unity yet, it's slower, and we want to attract AAA developers, for example, AAA games, and if we are not able to provide the performance that are looking for, we will not be able to attract these developers. So CodeGen was an important aspect of it, of course. And the second aspect is memory, and if you have a good data layout of your objects or of your data, but your CodeGen is not able to fulfill this data layout, you are not going to get the best performance that you could have. So if you have good data layout and you have good CodeGen, it's going to work beautifully, and that's what we are trying to do. And that's one thing that I keep saying when we talk about the difference, for example, with Java, is that in C# today we can use value types, we can use structs to have a good locality of the data, to control the locality of the data, and that's fundamental when you want to develop something that is leveraging the CPU, the caches, and so on. So that's one of the super nice feature of C# and the .NET ecosystem, actually. And also the GC, of course, is an important part of it. And that's why we are not using the GC or managed objects in Burst. But for me, usually the GC is not the problem. It's more like the allocations that we have in our programs that are the problem. So maybe we could avoid these allocations. Maybe we could do them differently. So memory is super important with CodeGen, actually. There are other reasons why we have been developing Burst. Another very important aspect, and this is not yet part of Burst, we are going to work on it, it's having deterministic results for floating point operations. So it's very important, for example, if we want to synchronize physics across devices, remote devices, for example, between a server and a client, and you want to have an exact same execution and an exact same simulation of your code across devices that have, for example, different CPU architecture. And so that's one of the important aspects we want to do. And of course, we want to stay in C#. We love the language. We love the productivity that we have with that, with C#, and we want to give the same experience to our users. So we want to bring JIT with our compiler technology, and we want to deliver the JIT as a package so that people can upgrade them when we have some bugs. And yeah. So how Burst is working? That's the timeline of the project. It's something that we started last year, at the beginning of the year. We did a prototype, and with this prototype, we did a show at Unite Austin. That was the first picture I show you about like the 200,000 agents. And then we took a step back and we started to work on Burst. So that was the real project. But before that was a compiler prototype. So we were experimenting stuff, and that was very important to do this during this part. And since then, we have been releasing 40 releases of Burst since its launch, mostly to bug fix everything, and to bring a few optimizations, of course. And we released a preview of the AOT compilation mode in July, just earlier this year. And all of this is about a new paradigm that we want to, mantra that we want to push at Unity. And that's what we call performance by default. So we want our users to be able to develop games, but get performance by default for the games without much trouble or much work from them. So the compiler is composed of different parts, of course, and it's quite standard. We have a front end that is responsible to translate IL to Burst backend calls. And we have both a JIT and the AOT are using the same front end, but they just interact differently with it. And inside Burst, we have what we call a Burst backend that is going to interact with the Burst LLVM, which then is going to interact with the LLVM code directly. And so like it's a work where we transform the IL to some IR at some point. We have here, we transform the calls to some burst AR, if we could call it like this, And then at the end we have some native code. That's a Sun that's very compressed fusion and very fast. And so today we are able to run on platforms like Windows, Mac, Linux, PS4, Xbox One, iOS, Android, and this yep. And so one of the questions that I had someone asked me this question actually yesterday. So why are we using IL, for example? It's quite simple. The IL representation that we have, so the IL is the intermediate language that we have in the assemblies in .NET. It's very easy to map this to IR, the LLVM representation. So it's very low level, and we will see that there is a small difference, but not quite small, but important difference. But still, the level is very similar. So in IL you have like an add instruction between integers, and in LLVM we have the exact same instruction. So it's very easy to use. We have also the tooling around that are very good. Cecil, for example, is one very popular library that we are actually using. And that's the same technology that we're using for our project that is at Unity that is doing IL to CPP. So convert IL to CPP code. And of course, you don't need source code. Rather, for example, compared to a solution where we would use Roslyn. And Roslyn, of course, is making lots of transformation to the code. And if we wanted to plug into Roslyn, we would have to plug into a place where these transformations happen into Roslyn, and that would be more difficult. Burst also is working on a subset of C#, and as I explained, we are mostly removing the usage of managed objects entirely. So it means that you have still your beloved primitive types, hopefully, and the enums, the struct, the pointers, and two other types, but that's the only thing that you have. And then, for example, if you want to use an array of some memory, we are providing some high-level types, like a native array, and that's our replacement of a managed array, actually. And we'll see that the native array has also some additional benefits that for example, we don't have with a managed array. And so we are able to handle all the control flows, the basic support for through exceptions, and we call this subset HPC sharp. So if we find something about this, that's the word, the acronym that we used. So it means high performance C#. And the work on this is not to ask our developers or users to modify their entire code base to write into this subset, but just to focus on maybe the 20% of their code that is taking 80% of the time of the game. So most of the time, when you optimize the tight loop, the loop in your game that is like taking quite a huge amount of time, that's already the best you can do sometimes. There is also something that we have been using at Unity that is called IL2CPP. So that's the solution that at Unity that's our AOT solution at Unity that is transforming IL to CPP code so that we can run our .NET code on platforms that don't have any kind of JIT, for example. And the problem is that IL2CPP was designed in the early days to run stuff on games on iOS, and it was not designed for performance. Of course, it's a general purpose compiler, general .NET runtime, and for us in Burst, it was a lot more easier to experiment optimization that we wanted to try. For example, the way we are handling mathematical functions, I hope I will have time to show this, or experiment even LLVM customization that we want to do. But we could share of course, some core components maybe at some point. So it's not like completely, and we are using their linker actually to generate the final executable. Another question that you could have is why LLVM? So LLVM is super easy to use if you want to try to write your own compiler. I think that Imo Landvert at the C# team is writing currently a small YouTube courses about writing a full language from scratch, and he might use LLVM, I think, maybe to generate some native code. So if you follow his talk, you will be able to see that it's very easy to use. And so, yeah, LLVM is great. It provides an amazing support for debugging. It's very easy to use. That's a library. It's used by Clang. That's a C++ compiler that is very famous, used by Chrome and so on. It's quite extensible. Even if you don't fork LLVM, you can still bring lots of optimization into the pipeline because it's pluggable. You can add your own compilation passes, even if you are not inside the code base of LLVM. And they have a good debugging community, huge community, and a good debugging experience actually. But the community is good. I went, they have like a huge maze list, so it's the whole way of working. I tried to ask some questions sometimes, I didn't get any answer. But I mean, when you have like serious trouble, I think that they are very helpful. So let's take an example. That's a very simple method with two arguments, left and right, integers. We add them, we return the results. And the IL, so that's the debug version. That's why there is a bit more stuff in it than usual. So you have like the load argument of one, of the second one, and we add them. And IL is a stack-based intermediate representation. So it means that it's using a virtual stack, and it pushes arguments on the stack, and there are like instructions that are going to pop these arguments and maybe to push something else, the result of it. So for example, that's the case for the add instruction. And in LLVM, it's different, but it's very similar. So it's register-based. So you have an infinite amount of registers. So for example, here you can directly declare left and right registers, and you can have like a local variable register, and then you can add them by passing arguments directly. So it's even a lot more easier to read than actually IL, because you don't need in your head to know the stack. That's very painful when you read the IL actually. And the generated code. So it's very simple. You have the left argument here, the right argument here, and this instruction that is doing the addition. And in this case, even this simple case is already asking a bit of optimization actually, because for example, usually you don't use this instruction to add two numbers in assembler. Usually you use the regular instruction like move one value to another, and you use the add instruction. And usually this is used more to move, to add pointers or stuff like that. But compilers are using these tricks to avoid this kind of multiple instruction, maybe an additional register. So even in this simple case, you can see that a compiler is already trying to optimize your code, actually. And we will see that it can be different depending on your compiler. So there is one thing that is important in the job system in Unity, is that we have been implementing a task like job system in the past years, and it's implemented in C++. It's struct-oriented compared to the task-oriented that we have in C#. So we don't allow managed reference. And but there is an important aspect of it, is that we are providing safe concurrency of data access. So when you have like some data inside a job, so for example, the native array that I was talking about, actually inside our native array, we have some structure that are providing safety, concurrency safety. So for example, if you launch two jobs with the same array, we will be able to, at runtime, to detect that you are actually maybe writing to the same native array concurrently, and that might be bad. So we are able to provide this kind of feedback to the users, and that's why we are using this kind of small wrapper around some unmanaged memory to provide safe concurrency. But that's not the subject of my talk, so I won't talk about it. But the important aspect of this is that not only it provides safety, but it provides also what we call no aliasing information. It means that it guarantees that all the input of your jobs are not going to use the same memory. So, and that's an important optimization that we can rely on later when we do the codegen. And another aspect, I will talk about it later, is that it's running on native threads. That's mostly because because of some mono restrictions that we had, and but it can still run managed code or native code. So in Unity, you can develop a job like this. So it's very similar to a task-based. The only difference is that you have a job, iJob, that's an interface. It has an execute method, and then you implement your kernel, your job. And it has some input, some output. You can, this one, for example, is just copying the input array to an output array. That's very easy. And then here we specify the burst compile attributes. So it means that this job, when it's going to be scheduled and later executed, we want these jobs to be burst compiled. And so we schedule this job, and in the internals, it's going to be a little bit dirty here, but actually we don't execute directly your execute method, but what we call is a wrapper that is going to maybe execute on your method, but maybe doing more things. So in this case, it's a job that is a single job, so we are just calling a method. But for example, we have a job that is called iJob parallel 4, and the execute method of this job is taking an index, and it allows us, for example, to have a batch of work with an index inside of a job, for example. So you can use this index, for example, to do some work related to index-based algorithm. And so and internally, we use this knowledge to say, oh, you have the iJob, but what we are going to execute, where we are going to compile is this method in the end. And that's where we schedule the system. So this wrapper method that contains the job is going to ask to some burst Unity integration. Can we compile to JIT? Are we in the editor? Yes, we are going to compile the method in the JIT, with the JIT. And if we are running in a game that is shipped, we are going to, instead of using the JIT, we are going to load a generated shell library that has been precompiled by the burst compiler here. So we have two modes, AOT and JIT. And for the JIT, of course, it's a JIT, so we want to be to compile the job on demand. So we compile the job when you schedule it, and that's different when you do AOT compilation. When you do AOT compilation, you need to figure out what you need to compile into your whole application, what you need to, all the jobs that you need to compile. So we have two modes, and that's why we are using an attribute that is here on the job that is used only by the AOT mode, and this attribute is able to link the job interface with this private method here that is going to wrap our jobs. So it's two ways to schedule the jobs, but we need to be able to recover this information of AOT. There is one thing about, yes, when we are talking about JIT, it's different from a JIT like a ReUJIT, for example, that compiles the first level of your code up to the method that can be inline. So ReUJIT, for example, is going to check, oh, can I inline this method inside the method that I'm compiling? Yes, okay, I'm going to compile it inside my method and so on. But then if there is a big method in your code that you're going to call, the JIT, of course, is not going to compile this method immediately. It's going to wait that your method is actually called to compile it. But in Burst, it's more like a hybrid model where we do AOT compilation for one method. So it means that when we compile a method, in this JIT mode, we actually do the full closure of the compilation. So we are going deep into all the calls, deep inside all the generics, instantiation and so on, so that we are able to compile a final executable that we don't touch anymore after. So in Unity, we have some burst inspector, and you can view on the left the jobs that we can compile, and on the right, you can see the actual generated assembler code, for example. And what we want to do with this burst inspector is to provide an optimization component tool where people will be able to spot the problems that they have in their jobs, so that maybe some optimization are not working, maybe the auto-vectorizer is not kicking in, and many other stuff. In terms of testing infrastructure, we have lots of compiler tests, of course, and usually unit tests are very important in any applications. But in a compiler, it's very paramount, because if you make a mistake in your compiler, that's not only your test case that you didn't make that are faulty, but all the user code, all the games that are going to act strangely or to have bugs and so on. So we need to be very careful. Of course, compiler bugs exist, and they are a pain to isolate. For example, in Coursera, they have like quite every month, maybe they have a bug sometimes, and it's they need to fix it quickly and so on. So that's very that's an important problem for compilers. But ideally, we would like to have zero bug, almost introduced by burst, and then if we have something that is not working, we would prefer to throw an exception and say, oh, I don't know how to handle this, rather than generate invalid code, actually. And the thing is, our work is simplified because Burst is just a kind of transpiler, so we are just converting from IL to IR. So the coverage, the problem coverage is a lot more simpler than, for example, translating from IR to native code, of course. And that's what we're going to see just after. And in our test, it's quite easy. We have like many small methods like this. It's using NUnit. NUnit is great for this because you can hack very easily their compiler, their testing infrastructure. What we do here is that we don't have any asserts. That's not like, it doesn't look like an NUnit test. But what we have is that we are going to compile this method and run it as it was a C# method. C# code, of course, with a JIT, ReUJIT, and so on. And we are going to compile also this method with Burst. And then we compare the results. And we do this for thousands of methods like this. So that's our way to check that Burst is correct. And we do also save what we call assembly gold images. So it means that for each test, we save to the disk some assembly code, and we compare them when we run the test with the latest version, so that anytime there is a changes in the code, and we can spot what we did wrong, if we did something wrong, or if the changes are relevant, and so on. Okay, so let's start with the optimization that we have with Burst. There are 4 parts that I would like to go through, and I think that I'm going to have to go quickly on this. So it's going to be like 7 minutes per part. Okay. So there is one part that is, of course, super important. It's the LLVM codegen compared to Mono.NET. Another part that is the Unity.Mathematics that we have. It's our equivalent of system.numerics.vectors, and the non-aliasing memory access that I talked about. That is important. That's something that maybe you don't know what it is, and I will be happy to explain the problems. And of course, there is one side that I would like to talk about is the native codegen and GC. How do they work together? So Burst is really the tip of the iceberg, and we are sitting on the shoulder of LLVM, really. If you look on the side, Burst is just here, and the whole part here is done by LLVM. So even in ReUJIT, actually, you have like many of these steps are actually in a compiler like ReUJIT. And most of, for example, the optimization that you could get is in IR transform, for example. That's the one that is going to do the constant propagation, the inlining of the functions, and stuff like that. But there are also like different aspects, like the register locator. That's the stuff that is going to tell, oh, I have an infinite number of registers, but now I need to map it to some like 16 registers. How do I do that? How can this be efficient? And this part, for example, is very difficult to develop actually. And there is another one that is quite difficult also, is the instruction selection. So, for example, the LEA that you saw before, that's the kind of work that the compiler needs to check. Oh, LEA, yeah, can I use it in this case? Yes or no, because there are cases where you could not use LEA, for example, the instruction. So, yeah, all of these parts are very important. And if we zoom into higher transform, that's what LLVM today is doing. And that's a bit a shame because I didn't do this work, but I should do it. Is when you look at ReUJIT and at this optimization that you have in LLVM, actually ReUJIT maybe has 1 entry per category or 2 entries. So it gives you like an overview about what kind of optimization that LLVM is bringing. And LLVM has like maybe the higher pass, they have like 134 1,000 lines of code. The analysis just before that is very important, has 40K lines of code. While, for example, Burst, we just have like maybe 20K lines of code. So compare to this work, that's where all the challenge is. So let's take a look at the example before. It's not really interesting, but just to highlight the difference that even on simple cases you can have. So we're going to have lots of, in the next slide, we're going to have lots of assembler. So I hope that you won't quit too quickly. So the thing is, yeah, if you look, Reagit and Burst, they are the same. That's great. Mono is slightly different, and it's a bit unfair in this example because I didn't put the full code because I didn't have enough space, but actually I put no inlining on this function in order to get the output of this function in Mono. So usually when you use a method like this in C#, it's going to be in line, right? And so you are going to you won't have a call like this. You won't have like a ret and so on. It's going to be in line at the call site. Here in Mono, it's the default Mono compiler, and they have been developing over compiler like using a Mono LLVM, so they can produce this kind of code. But the default Mono, for example, is generating this. For example, they are using stack to pass arguments. There is some kind of mistake where they load something but they don't use it. Well, this kind of thing. So let's look at something simple. Binary search. It's a very small code. That's something that you have maybe used already, it's optimized quite. Burst is actually 10% slower than Reagit. So what's going on? Actually, that's the pinvoke. So when you use pinvoke, always check that the C++ code that is going to run behind has enough work to do, because there is a cost to switch from C# to C++. So when I see some C++ code and it's very small, and you call a pinvoke method, most of the time it's going to be to perform worse than what you could have done in C#. But what we can see is like Mono is performing a little bit. Plain Mono is already a little bit slower, and the Mono LLVM AOT, we have LLVM backend, is actually even better than Burst, because they don't have this transition that pinvoke has. If we look at something a little bit more complex, it's Mandelbrot. So it's simple, but there is a tight loop in Mandelbrot. So you have usually in Mandelbrot you have a loop on the x axis and a loop on the y-axis, or the opposite actually, and there is this small loop that is going to generate this little pixel information that is building the shape of the Mandelbrot function. And here we can see that already, for example, Reagit is a little bit slower and Mono is significantly slower, but Mono LLVM is actually as fast as Burst. And what's happening is that, for example, in Mono, lots of registers are unused. They are using the stack lots. So it means that, for example, the register allocator, the part that I showed previously, is quite weak, for example. While with Reagit, the code is actually quite good. You don't have any stack around. And actually, when you look a little bit deeper, you can see that they are still loading two constants. That's 2 multiplied by 2 and multiplied by 4 that are in this small loop. But it's still very good, actually. But already what you can see is that Reagit is starting to allocate more registers than Burst, than LLVM, actually. So the code here is starting to be a little bit more optimized. So let's look at one optimization that we have in LLVM that, for example, Ryujit doesn't have today. That's one code that you may have had in your code base where, for example, you have an argument where you have a Boolean, and maybe inside your loop you are going to check, oh, should I do this or not? And you do this inside a loop. And and maybe inside this loop you have some work to do, and involve a loop. It's simpler, for example. So the loop and switch optimization in LLVM is able to extract this loop and to create two loops, and to extract the condition that was inside your loop, to extract it outside your loop, because it's an invariant, for example, in this case, and to duplicate the loops so that we have two fast code paths. And what we see is already that in that case, if we pass true or false to burst, we are going to see quite some difference, actually. So that's the kind of thing that on micro benchmarking you won't see. Sometimes, for example, for the binary search, you don't see this kind of stuff. But if you start to have this kind of code, you would see this kind of difference. And so on the left, the codegen is well optimized, and there is no variable spilling on the stack and so on. And so it means that the check inside the loop. So the codegen of Ryujit actually is quite good here, but even that it's hurting quite a bit the performance actually. And if you look on the other loop, it's even more dramatic, like 6 times slower with Ryujit and 16 times slower with plain mono. But the mono LLVM is actually getting back. And some of the optimizations that are behind are, for example, auto-vectorization that you get with LLVM compiler. So if we look at count bits, that's another example, and Egor is here because he suggested this when he played with Burst. So I thought that it was a good example about some optimization that you get with LLVM, for example. So count bits is something very simple where you have like something that wants to count the 0 bit in an integer. So it might not be very useful, but quite some time you can have some algorithm that can use this kind of techniques actually. And here we have a small function that counts a bit for one integer, and we have the full function that is going to reiterate for example, on a large array, and it's going to calculate, for example, all the bits that are in this large array. So here, the difference are starting to be quite dramatic. So we have like 9 times slower, 10 times slower, 7 times slower. And what's LLVM is doing? It's generating this kind of code. This little loop is just massive. And the reason is that they are auto-vectorizing your code automatically for you. And this single function that you have here, like the count bits, it is translated to a single instruction here that is pop count. But then LLVM is able to see that we are using also this pop count instruction into a loop, and it's no longer using this pop count instruction, but it is using some SIMD instructions to perform these operations. And they are using like bit patterns, and they are working on multiple integers. So they are processing 16 integers per loop. But you get this for free, actually. You don't need to change your code. You don't need to. And in .NET today, if you want to do this, you need to do it manually. So you need to use system.numerics.vectors. You need to use the new hardware intrinsics that are going to be added to .NET Core 3.0. But that's very laborious to do. And with LLVM, that's the kind of optimization that you can get. So to recap, like the LLVM optimization are very important, and for in our case, we are able to rely on them because we are working on a subset of a language. That's a subset that can be useful for, not only for games, but that could be useful for many workload where you work on data, like AI, typically. So it provides lots of optimization. But there is, of course, a downside of it is that the LLVM compilation is very slow. But as we are working on very tight loops, it's less an issue, actually. So another aspect of it is what we have been doing with Unity.Mathematics. And so Unity.Mathematics is providing SIMD types. So it means that, for example, we have a float 4, float 3. So they have like, there are structs in C# with 4 floats, for example. And that's the equivalent of the system.numerics.vectors. And that's very important to use this kind of registers and stuff in your code because, for example, on ARM and Intel, for example, you have lots of these registers directly accessible in the processor. So it helps a lot to lower the register pressure that you can have in a program, because it means that you can store, you could store in live in a loop or whatever, like 16 multiplied by 4, so 64 floats in a CPU. GPU, for example, they have like 15 megas. Some of them can have 15 megas of not register, but bytes for registers. So like CPU are very small compared to GPU, but it's still helping a lot. And of course, we have some downsides. So for example, there is this problem where in C#, because it's 4 floats, we need to treat this struct of float as 4 floats, an array of 4 floats actually in LLVM. But when it's on the stack, we need to say that it's a register, and we are working with a register. So it's an annoying pattern, because usually when you, for example, you do GPU programming, for example, a float 3 here is going to occupy a full 16 bytes, actually. It's not going to be 3 floats, it's going to be 16 bytes. And that's annoying for us, because we still want to have only 3 floats in memory. We don't want to waste memory. So we need to convert like the small representation that we have in memory to this register. So when, for example, you use this kind of float 3, int 3, or float 2, for example, usually they are not very efficient, while this one are more efficient. And I think that RealJIT has the same problem, actually. Never look at it, but another aspect that we have are intrinsic function, and that's something that you don't have. I mean, not like this in RealJIT. So, for example, we are providing lots of mathematical functions. So, for example, cos and so on. But we are providing SIMD version of this mathematical function, for example. So you can, for example, do a cosinus on 4 angles at the same time. And this can be important, like for example, when you calculate a matrix with a free looking direction, you need to pass 3 angles, and you need to calculate 3 matrix, or 3 cosinus and sinus. And in this case, we can, with just a single instruction in burst, compute the whole stuff. But then we map stuff directly, instruction differently to LLVM. So in some case, we don't use anything special. We convert to C#, from C#IL to LLVM without doing anything. But in some case, we can say that, oh, this function, we have actually an LLVM intrinsic that is available, so we can call it directly. And for more complex functions, like the cos, for example, we are calling we are actually using a SLIF library that is a SIMD library written in C++. What we do is we convert this library into IR, and then we inject the IR into our code base. So it's kind of what they call LTO. It's kind of linked time optimizations. So we are able to bring a large part of code that are highly optimized, but it's in LLVM, and we can link this with our functions. Another cool thing that we have that you don't have in C#, for example, is we can specify in our jobs the accuracy and if we want to relax the floating point operations. So for example, accuracy is like how many bits I want for my cosinus. Maybe like 15 bits is going to be enough. And depending on your requirement, you could require, you could balance with less precision but a faster code. The same for relaxed operation. It's called fast math in C++, and it means that you can actually reorder the mathematical operations so that you can collapse them. And usually you don't do that with a floating point operation because the order is very important, because otherwise you're going to get different results, for example. So that's the kind of optimization that we are able to do. And the cool thing is that on the same kind of code, for example, here I have one job that is using some share library, and I have another job that is using exactly the same share library. But what we can do is that we can generate some code that is going to use the full standard precision, and we can run a job that is going to compile this function with lower precision. And that's kind of cool because you don't need to rewrite your code. It's just that it's going to say, oh, I want one version of my function that is poorly optimized, but very fast. And for example, I'm going to use it for game elements that are very far away from the camera. I don't care about the precision, and that's fine. But for elements that are very close to the camera, you want maybe maximum precision. So that's the kind of thing that you can do. And if you had to do this in C++, that would be very painful to do. You would have to play with a compiler. You would have to use some if-def and processor stuff to do that. So we can do this quite easily. Okay, 10 minutes for the two parts. It's going to be difficult. I will maybe skip some slides. Memory aliasing is one very important problem in compiler, and with your code too. So memory aliasing is about when you have memory location in your code, and there are maybe multiple variables that are going to access this memory location. So by default, usually compiler, they assume that two pointers with the same type, for example, they are maybe going to alias. So it means that maybe they are using the same memory. And if I take this example that is very not interesting at all, but it's going to help to understand that, for example, there is a variable A that we are going to copy to the variable B here and C. And what's happening here is what you get with a reujit, for example. So on the first assignment of A to B, it's going to fetch the value from A and copy it to B. That's fine. But then, assuming that nothing changed, it's still going to load again A. It shouldn't change. And it's still going to copy. Of course, it's going to copy it. But if you are able to give to the compiler, to your arguments, for example, that says, oh, A is not going to alias with B and C. I'm sure that it's not going to alias. The compiler will be able to generate this kind of code. So it just saves one instruction, right? That's okay. What a single talk to talk about just one instruction that we're saving. No, the thing is that when we talk about arrays of data, this is going to be super important, because in that case, the compiler won't be able to optimize your loop. And I'm going to go directly to this schema. So, for example, this loop is just like copying like floats value to an output array and just multiply by 2. And when you don't have any aliasing, of course, everything is very simple. So the vectorized version of your code is going to run fine, right? But if you start to have some aliasing, so it means that, for example, your buffer here is actually overlapping part of your input buffer, for example. So if you start to do the scalar version, you're going to have some results, but the vectorized version, exactly the same code for the scalar that I showed before, is going to be completely different. So the compiler, if it doesn't have any information, it won't be able to say, I can vectorize your code. So most of the time, it is going to say, OK, I'm not going to vectorize your code because I cannot guarantee that I can do this safely. That's not entirely true because compilers are now, today, generating if-def at the beginning, and they check if the arrays, they overlap, actually. And so, for example, this is the kind of loop that is generated, and with a scalar code, and with auto-vectorizing code, that's the kind of code that is generating. So they compare at the beginning, do we have enough elements? So if we have enough elements, we can maybe process 32 elements per loop, and otherwise we are going to process remaining elements. And again, you can do this with Ryujit, but you have to do it manually. And yeah, so that's I'm going to skip this. One important thing I would like to talk about this is this, because that's something that is maybe not very common to hear about. There is an important aspect of native code and GC and how they work together, and it depends on the compiler, the JIT and the GC that you have. So in this example, I would like just to show you that we are going to run not only some data-oriented code, but we are going to run some regular managed code using Markdown, one library that I wrote, Markdig, that is going to convert some Markdown document into HTML, all in memory, so lots of allocations, even if Markdig is quite optimized and so on. So it's using lots of reference types, and we are like running in a loop, converting Markdown documents, so lots of allocation. And in another thread, we want to run some Mandelbrot, so that's the code that I showed before. Mandelbrot, only compute, no manage objects, and what's the results of this? So on the left side here, it's the mono-threaded version, so I took it as like a baseline. So it means that the code in Markdown has a value of 1 when they run separately. Okay, if you run Markdown separately, it's 1. If you run Mandelbrot, it's 1. Now we start to run both of them at the same time in the same CLR, and you can see that Mandelbrot is starting to be slower. And what's happening is that the GC is going to stop the managed thread because there are like allocations all around. And that's very annoying. And when you look at burst, actually we don't have this pattern, and we are able to be 10% faster than what we had, previously, but now we are 20% faster than this version. And the reason is that the GC is no longer stopping our job, that is doing pinvoke work. And the reason is that the core CLR GC is very efficient, and it will process only a part of a stack that is concurrently, it will pass your stack that is managed before the pinvoke, but it will not stop the native thread, actually. And that's super nice. But that's something that you don't get with all the runtime. So for example, with Mono, if I run the same thing burst within Mono, for example, and I have a managed thread that do lots of allocation, it's going to be slower, like 20% slower. And I'm running out of time, so I'm just going to skip it to the future. We want to bring DLL import. We want to support managed array for read-only static data. We're going to work on deterministic. We want to improve the debugging experience and so on, more performance, some LLVM improvements. So maybe we're going to have to fork LLVM. And hopefully, I hope that we will be able to open source it, I hope. And for .NET, what does it mean? So tiered compilation is one of the important stuff that is coming, and that might be, we might have some opportunities to bring some of this optimization that I showed in some more aggressive optimization that we could have in some scenarios, tiered scenarios. So that's a good thing, because with tiered compilation, we're going to be able to bring more optimization. Cohort also is going to benefit tiered compilation, so that's cool. There was a project called LLILC that was using LLVM, so that's one possibility. And there are like crazy solutions that you could think about, like, oh, we could use IL to and LLVM to optimize the IL. It generates some optimized IR, for example, and then we write back this IR to some optimized IL, actually. And so we could generate optimized IL very easily. And that's all. Sorry.